Okay, we are going to be doing some physics. So, first problem. A child of mass m is exerting a tangential force F on a merry-go-round with a moment of inertia I and radius r. So kind of get this picture in your head, you know, when you're a little kid at the playground, and, you know, there's this merry-go-round, and so you would push this merry-go-round around in a circle, and with this force, as described here. And so that would get the start to spin with an angular acceleration, right? And so the first part of this problem is to calculate that angular acceleration alpha of that merry-go-round. And then the second part is to find the angular velocity omega after a time t has elapsed. C is calculate the work done, so the work that the child does pushing this merry-go-round and getting it to accelerate. And D, what is the total kinetic energy of the merry-go-round after the child, the merry-go-round and the child, the whole system, after the child has jumped onto the edge of the merry-go-round. So the edge meaning that the child is a radius r away from the center of rotation. So first part, calculate alpha. So here's kind of your little picture. Here's the merry-go-round. Here's the radius, the moment of inertia, and this F. And so I just set this coordinate axis being counterclockwise is positive because that just fits. The torque is going to be positive because R cross F, and so it points out of the page, and so that's positive. So Newton's second law for rotation, kind of thinking analogously, where torque is kind of like force in linear, moment of inertia is kind of like mass, where it's just resistance to change, and angular acceleration is akin to linear acceleration, A. So torque, R cross F, equals I alpha. RF sine of 90 degrees because it was a tangential force, and sine of 90 is 1, so we can pretty much eliminate that. And just doing some algebra, we get that alpha, the angular acceleration of this merry-go-round, is RF over I. So, moving on to the next part, calculate omega after a time t has elapsed. So, remember in linear we had v equals at, well, omega equals alpha t. And we know alpha from the last part, and, you know, just plugging that in, and we get omega equals the radius times the force that the child exerts times the time at which the time t that has elapsed divided by the moment of inertia I. Part C, calculate the work done. So work, energy, okay, well we know conservation of energy. And so we have an equation for that, and here is this equation. The initial potential plus the initial kinetic plus the work done, and it's this work that we're trying to find, equals the final potential plus the final kinetic. Well, initially there's no potential energy, you know, there's no gravity, it's not falling or anything. There's no kinetic energy, it was stopped at the beginning, but there is some work, and so we're trying to find that work. At the end, there is also no potential energy, however there is kinetic energy, and that kinetic energy is 1/2 I omega squared, like 1/2 mv squared, 1/2 I omega squared. So plugging in for omega, we get 1/2 I this quantity squared, and so just doing some simple algebra, we get that the work done equals RFT quantity squared divided by 2 I. There is also an alternate method of doing this. We know in linear that the work done by a force on an object is is the force times the displacement. So in rotation, the analogy is work equals the torque times the angle over which the object was displaced. So we can calculate the angle. Also, there's this equation, which is, you know, very, very familiar because we know that the change in position, in linear position, equals the initial speed times time plus 1/2 the acceleration times time squared. And so just substituting the analogous quantities, the change in the angle equals the initial angular velocity, which is 0, times time plus 1/2 alpha t squared. So, just doing some algebra, we already know what alpha is. We get that the displaced angle is RFT squared over 2I. So, and then we also know what the torque was, and so we just plug in, do some algebra, and we get that the work is RFT quantity squared divided by 2I, which is the exact same as this. So it's two methods for the same answer. Now the final part of this problem is to find the total energy of the whole system, which includes the merry-go-round and the child. So total kinetic energy equals the kinetic energies of the merry-go-round, case of M, plus the kinetic energy of the child, case of C. Well, case of M we just solved for in the last part. In case of C, we can find out just as easily. So the general formula for kinetic energy in rotation is 1/2 I omega squared. Well, I is the mass of a particle multiplied by the square of the radius about the rotation, the point of rotation. So since the child is at the edge, then that means that its radius about the center of rotation is r. Therefore, it's 1/2 mr squared times, well, it's got the same angular velocity as the merry-go-round. So we already know what that is, and so we just plug it in, finding that k sub c equals m times r squared ft quantity squared divided by 2I squared. So plugging that back in, doing some algebra, we finally get that the total kinetic energy of the merry-go-round and the child is rft quantity squared times I plus mr squared divided by 2I squared.